purchase a good health by paying money, but BioHeal 2023 will try to offer it at no cost. Furthermore, one can also explore the beauty of Rishikesh and can get golden opportunity to see Ganga Aarti near the banks of river Ganga by being staying in the Parmarth Niketan. In addition to that, as you know, the Parmarth Niketan is quite famous for yoga, pranayam and other activities. So you can also have your peace of mind and other recreational activities also you can do here, along with getting insights about the healthcare industry and tissue engineering applications. Now, I would like to welcome all the dignitaries on the dais. First of all, our chief guest, Dr. Minu Singh, who is currently AIIMS Director, AIIMS Rishikesh Director. So please welcome her on the stage with big round of applause. Secondly, I would like to call upon Dr. Pradeep Srivastava, who is currently Director of DIFSS. Nextly, I would like to call Professor Yusar Zhang. He is an adjunct jointly faculty at National Siang Hua University. Professor Pralay Mathi, Professor IIT BHU Varanasi. Professor Sujata Mohanty, Professor Stem Cell Facility, DBT, Center of Excellence for Stem Cell Research, AIIMS, New Delhi. Professor Gopinath Pakrisamy, Professor IIT Roorkee. Professor N.C. Mishra, who is also the convener of this conference. He is currently Associate Professor at IIT Roorkee. Professor Bhisham Narayan Singh, Assistant Professor, Manipal School of Life Sciences, MAHE, and he is also the co-convener of the conference. So now I would request all of the dignitaries to please lighten up the lamp and just proceed the conference further. Now, I would like to invite Dr. Narayan Chandra Mishra, convener of the conference, to felicitate our chief guest, Professor Meenu Singh, Director, AIIMS Rishikesh, with beautiful token of appreciation. Dr. Meenu Singh was trained as a pediatric pulmonologist at the Children's Hospital, University of Pittsburgh, USA. Since then, she consistently worked in India in the field of pediatric pulmonology at the Advanced Pediatric Center, PGIM at Chandigarh. Now, I would like to request Dr. Bhisham Narayan Singh to felicitate our guest of honor, Professor Pradeep Srivastava, Director, TIFAC. Professor Pradeep Srivastava is the Executive Director of TIFAC. Prior to joining TIFAC, he was Professor and Head School of Biochemical Engineering, IIT BHU, Varanasi. Now, I would request Dr. Narayan Chandra Mishra again to felicitate Professor Yusar Jeng. He is an adjunct, jointly faculty professor at Nasang Siang Hua University. He is having major expertise in the Radiation Research Center. Now, I will request Professor Bhisham Narayan Singh to felicitate Professor Pralay Mehti, Professor IIT BHU, Varanasi. He has been working in the areas of polymer nanocomposites, biomaterials, self-assembly. Now, I would request again Professor Narayan Chandra Mishra to give the token to Professor Sujata Mohanty, Professor Stem Cell Facility. She is currently working as a professor and principal investigator. Now, I would request Professor Bhisham Narayan Singh to felicitate Professor Gopinath Parkiswamy. Now, I would request Professor Narayan Chandra Mishra to felicitate the co-convener of the conference, Dr. Bhisham Narayan Singh, with the token of appreciation. And I would invite Dr. Sharda Partha Malik to provide the token of appreciation to Dr. Bhisham Narayan Singh. नहीं. Okay. हाँ. So I would invite Dr. Shraddha Partha Malik to felicitate Dr. Narayan Chandra Mishra with the token of appreciation. Dr. Narayan Chandra Mishra is currently working as an associate professor at Polymer and Process Engineering Department, IIT Roorkee. Now, I would invite Dr. Narayan Chandra Mishra for the inaugural address and lightening up the theme of the conference. Thank you.
Good morning. Namaste. I invite all the divine souls present in this August ceremony in the conference BioHeal 2023. BioHeal means biomaterials and healthcare. Long ago, some professors were discussing how we can relate the spirituality to science and technology to enhance our knowledge beyond the limit. And the BioHeal, because of that discussion only, 4 years ago we discussed, and by that time Corona appeared, and most probably now Corona disappeared, so BioHeal now started. And in BioHeal, earned by the nature, that is air, purified air unit, pure, and then in the sun. We say Panch Indriya. So the next is the sky. From the sky, different signals we receive, where from different thoughts are generated, and then we work in different directions. We develop technology, we develop science, and that's why we are here now. So this place, as it is famous for yoga, and I thought if we are not healthy, it involves drugs, drug delivery material, biosensors, biomaterials, water purification, air purification, soil purification, digital health. So all the topics related to health here covered so that we get conscious about our health and we take care of health. We give enough time for our health, at least 1 hour every day. And here I am grateful to all the dignitaries, especially our chief guest, Professor Minu Singh, our guest of honor, Professor Srivastavji, and Professor Jane came from Taiwan. We have co-convener from Taiwan, Professor Chapu Chou. Somehow he did not get the visa, only today morning he got the visa. Tonight he will come here. So we are missing him here. And Professor Praloy Maiti from IIT BHU, Professor Sujata Mohanty, Professor Gopinath, Professor Bhisam, and all the delegates, all the students, and to all of you, I am very grateful that you are here to make a successful event, BioHeal 2023. Thank you.
After a wonderful talk by Dr. Narayan Chandra Mishra, I would like to call upon stage our chief guest, Dr. Minu Singh, to say a few words to all of us and motivate us. Please.
Hello.
Hello, yeah, thank you. So, first of all, I like to uh, express my thanks for inviting me to this beautiful spiritual place, Parmarth Ashram. We do come here very often when we meet Muniji, Swami Chetananda ji, and Sadhvi Saraswati Bhagwati ji, who are not present here today, but it looks as if they are present here spiritually. And they were actually, in Delhi. So first of all, I would like to thank God for inviting me, getting me this opportunity to be here with all of you. So Professor Pradeep Srivastav, who's the Executive Director of TIFAC, and Professor Sujata from AIIMS Delhi, Professor Gopinath from IIT Roorkee, and Professor Bisham from Manipal University, and of course our Professor Zen from Taiwan, and Professor Praloy from BHU, IIT BHU, and of course Professor N.C. Mishra, who is from IIT Roorkee and has organized this very important conference called BioHeal. The name itself is so good that you try to heal people, rather than just treat them with some medicines or with drugs or implants or all the treatment modalities which are there. So healing actually is very important. And sometimes the doctors also need to heal themselves. And because there is so much exposure of doctors to illness and also to people who are in misery sometimes, that your psyche also gets affected. And you need to build in a lot of resilience. And that resilience actually comes from a recourse to spirituality. And spirituality, I think we need to study scientifically. I don't know whether we need to or we should not, because this is something which does provide a new pathway for people to live their life. Along with that, we have several luminaries here who have experiences in different fields. And just before the conference started, I met Dr. Gopinath, who is a pioneer of nanotechnology at IIT Roorkee and has been creating several materials, nanomaterials, which are useful for medicine. We have Professor Sujata, who is working with stem cells, and we know that stem cells have a lot of future in medical science. And these days, this is the time of artificial organs actually developing through stem cells. And stem cells, as you know, can be programmed and they can be homed to different organs where they start working like the organ itself. And actually, I'm not very aware of the fields which you are associated with, but I have been associated with pediatrics, with children. And I do feel that we should be working for the betterment of children here in Uttarakhand, where we found that the mortality rate of children and actually the infants is more than the national average. So we need to have systems to monitor our mothers, follow them during pregnancy. And Professor Srivastava, it will be really useful if we get some systems where we can remotely monitor the mothers and the children in a serial way so that we ensure a healthy childhood to all these children who are there, and the mothers also, for them also we need to have healthy motherhood. So this particular conference, I'm sure, is going to get us into new vistas which are there unexplored. And many of you students whom I see, you are going to be involved in this kind of research, because next 20 years, I think biomaterials and smart materials are really going to grow. And same is true for artificial intelligence, because I think artificial intelligence is going to form a basis of developments on all these fields, because as we progress with data collection and data science, we will be able to develop models where we can program even lives, after they have been developed, and that will be a big contribution to medicine as well as to health and healing. So with those words, I thank all of you, and thank you, sir, for inviting me. And I really congratulate you for organizing single-handedly. I could see the way you conducted everything. You were, I think, doing everything all by yourself. So with all, of course, the blessings of the God. So thank you very much. Thank you.
Thank you so much, ma'am, for your wonderful words and motivating us. Now, I would request Professor Narayan Chandra Mishra to felicitate ma'am with the memento. Now, I would like to invite our guest of honor, Professor Pradeep Srivastava, Director TIFEC, to say a few words.
Good morning to one and all. Namaskar. और हम अगर आदर से आप सबको प्रणाम करना चाहेंगे तो मेरा आप सबको प्रणाम. I'm really very delighted to be here this morning and on the call of my friend Professor Mishra, who called me some times back, and look forward for my availability over here for this very interesting international conference, BioHeal. I thank Professor Mishra for having me invited over here and hosting me here since yesterday night to this beautiful place, Parmarth Niketan. The dignitaries on the dais, Professor Meenu Singh, Director AIIMS, Rishikesh, Professor Zheng from Taiwan, Professor Mohanty from AIIMS, Professor Maiti from IIT, my own friend, Professor Gopinath, and my young colleague, Professor Bisham Singh, and the dignitaries present in this hall. At the outset, I'm really very delighted to say that it's a great initiative in a small step to organize a very focused meeting on health engineering. And to call it BioHeal, I think there can't be any better word than this. When we look forward for healing of mankind, for healing of tissues, for healing of life. And what could be much better a place than other than Rishikesh, which has been involved in the spiritual healing of the mankind. So, as I said, really it's a great initiative. For the people over here, I'd like to just give a small introduction about my institution, that is TIFAC. TIFAC is an acronym of Technology Information Forecasting Assessment Council, the institution which was created by none other than the visionary, the legend, Dr. APJ Abdul Kalam. It's an institution, autonomous institution of Department of Science Technology, which works towards identification of forecast and forecasting of futuristic technologies, assessment of those technologies, and demonstration of those technologies for the cause of the nation. And why I'm referring to this institution first, because TIFAC has developed Technology Vision 2020, which has talked and which has referred to tissue engineering as an upcoming technology for the cause of the nation. We know that healing process of any illness or a human body can be manifested at various levels. If we are in the healing process using medicines, drugs, pharmaceuticals, that used to be one of the oldest process, followed by healing process using some biologicals, biopharmaceuticals, and then after graduating to a new process of tissue engineering, regenerative medicine. And more to come when we have organ on a chip and technologies therein. Today, this morning, as we all know, the science of tissue engineering, which was initiated in the year 1998 by the two people, Robert Langer from MIT, USA, and Joseph Vincati, a surgeon. So this happens to be a true marriage between the two streams of studies, that is medicine, engineering, and medicine. When we say broadly medicine, we mean including surgeries as well. And that's how the health engineering comes into play to serve the humanity, to serve the life. We all know about the Vinacati mouse, which had a lot of criticism from the society because the Vinacati mouse had a ear pinna attached to the back of the mouse, and which did involve tissue engineering, culturing of the collagen on the cells. Friends, today the tissue engineering and regenerative medicine has been taking leaps, strides, leaps and bounds. We have various streams of science and technology which are getting immersed into tissue to develop further tissue engineering. To mention cell culture engineering, to mention molecular biology, to mention chemical engineering processes. And all these streams together, they happen to add a new dimension, a new vista to tissue engineering. We know today we are talking about the 3D culturing of cells. And if you talk about the 3D culture of cells, you need to talk about the biomaterials. You talk about the biocompatibility. You talk about the bioavailability. You talk about the strength and all that. So the domain of tissue engineering has encompassed all that what you see to be included into it. You are culturing cells. We are culturing cells in the reactors. We talk of the new reactors, we talk of new designs of the reactors. We talk of computational fluid dynamics. You talk of microfluidics. You talk of AI. And all that, whatever you think this world could include, can be included into the mega dimension of tissue engineering. So young friends, when I'm telling all these things to you, I mean the young research scholars who are here this morning in this hall should definitely take a lot of initiative into these streams and can definitely contribute to in a bigger way for the tissue engineering. We are working on tissues to include hepatocytes, we are working on chondrocytes, we are working on the osteoblasts, we are working on the skin regeneration and many such things, to nephrons, neurons, and all that. And the interesting part is that we are trying to do a big supportive favor to the humankind, to mankind in the society. And in the process, we are not harming any animals. And the beauty of the whole system of tissue engineering is that you are developing, you are supporting, you are healing. And what can be the better service to the mankind, to the society, to the human being, other than supporting, healing, and treating, and making them free of any disease, free of any issues, and making them survive along. So I think this conference, BioHeal 23, will definitely find a lot of presentations, a lot of deliberations to come in, where new technologies will be discussed, new methodologies will be defined, and new processes will be designed for healing the humankind. So with these words, I thank the organizers, Professor Mishra and his team, Professor Bhisham Singh, who has come all the way from Manipal. I'm very happy to see you all. Thank you.
Thank you so much, sir, for your wonderful words. Now, I would like to invite Professor Bhisham Chandra Singh, sir, to felicitate Professor Pradeep Srivastava. now, now it's the time to just end up the inauguration session, and for the closing remark I would like to call Dr. Bhisham Narayan Singh sir to just give the closing remarks.
Very good morning to all. As we conclude this inaugural ceremony for BioHill 2023, I want to express my gratitude to Professor Meenu Singh, Director AIIMS Rishikesh, Professor Pradeep Srivastava sir, Director TIFEC, Professor Pralay Maiti sir, IIT BHU, Professor Jeng from Taiwan, Professor Sujata Mohanty ma'am from AIIMS, New Delhi, Professor Gopinath sir, IIT Roorkee, and the convener, Professor N.C. Mishra sir. Thank you. Thanks a lot, sir. I also like to thank all the delegates who joined the BioHill and the students as well, who came from various far away places or different states from different institutions all the way and joined BioHill 2023. Some of the delegates and students are on the way. They will join us by today evening also. Though BioHill, we hope to foster the collaboration, share knowledge and best practices, and identify new avenues for the research and development in tissue engineering. We are committed to building a community of experts and practitioners who can together address the most pressing challenges in this field. As we move forward from this ceremony, let us inspired by the possibilities that lie ahead. The coming days of the BioHill 2023 will be filled with the presentations, discussions, and interactions that will help us to chart a course for the future of tissue engineering and healthcare. We have the opportunity to create a world where tissue engineering, the biomaterial, the healthcare-related drug delivery systems, or other technologies, we have the opportunity to create a world where this all together, this field, whatever we mention, will help the peoples to improve their quality of life. Thank you for being the part of this historic moment in the field of tissue engineering, and let us begin BioHill 2023 with a sense of enthusiasm, curiosity, and determinations to make a meaningful impact. Together, we can make significant strides toward healing and improving life through the tissue engineering. Thank you all. So now I request you all to please stand up for a national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you. So now we will assemble all after 15 to 20 minutes and the invited talks will start. Okay, so now we can move. Or that way, that way.
कहती है बैठे तो मेरे रूबरू तुझको देखूं, इबादत करता रहूं। ओ आँखें कहती है बैठे तू मेरे रूबरू तुझको देखूं, इबादत करता रहूं, तेरे सजदों में धड़।
hello, check. Hello, 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 check, check. Hello, check. Hello, hello, check. Thank you.
Hello.
Hello, check, check. Hello, sound, test. Hello, check.
Hello. Hello. I request everyone to be seated. The talk will be starting in 5 minutes. Good afternoon. The first speaker for today is Dr. Pralay Maiti. Dr. Pralay Maiti is a professor and ex-coordinator of School of Material Science and Technology. Dr. Maiti has received his master's in chemistry from Indian Institute of Technology, Kharagpur in 1991 and PhD in polymer in 1996 from the Indian Institution of Cultivation of Science, Jabalpur University. He was researcher and lecturer at Venture Business Laboratory, Hiroshima University, Japan, at 1997 to 1999, and was a postdoctoral fellow at Tokyo Technological Institute, Japan, from 1999 to 2001. He was a visiting scientist at Cornell University, USA, from 2002 to 2004. He was Quick Hire Fellow at Central Leather Research Institute, Chennai, before joining the School of Material Science and Technology as reader in December 2004. He has been honored and awarded by APA Young Scientist Award by Asian Polymer Association, APA 2013, NASI, Reliance Industrial Platinum Jubilee Award by National Academy of Sciences, India 2018, Tata Innovation Fellowship 2020 by the Department of the Biotechnology, Government of India 2020. His areas of interest is polymer nanocomposites, biomaterials, self-assembly, biodegradable polymer, polymer for renewable resource, radiation-resistant polymer, fuel cell membrane, polymer electronics. We cordially invite you to the stage, sir.
At the outset, I would like to thank the organizer, especially the Professor Misra, for inviting me to talk whatever we are doing on the biomaterials, especially for the disease control. So this is a good platform where the science and spirituality meets, and we will be talking about the whole kind of the tree. starting from molecular synthesis to the healthcare technology. So, so we'll be talking about, actually in my group, so the time is short, I'll be very fast. So I'll be talking about the drug delivery vehicles for the disease control. So next slide, please. So next. So you can keep this slide up to this, okay? So this is the this shows that why there is a need for drug delivery. Whenever we take any pill, almost all the drugs are going to the blood streams, and that causes the toxicity, and that is serious. That whenever we are taking some drug for say antibiotic and other things, we have sometimes nausea or stomach problem because of this toxic range. So what is required is to find a drug delivery vehicles which can release the drug slowly to maintain the drug concentration at the bloodstream. That's the entire mechanism where we can effectively use the drugs for disease control. And there are several ways to do it. Either we can put this drug in the nanomaterial, we can put the drug in the polymeric materials, and we can functionalize the polymers, and how those polymers embedding the drugs can be say dissolved out or degraded within the physiological conditions to release the drug for effective disease control. So that are the different the mechanisms for the release concentrations of the drug in the bloodstream. So next, please. Next. Okay, so there are one way is if we use some of the biodegradable polymers, and then it will be biodegraded in vitro and in vivo to control the drug release. So that's what we have shown, that the drug release in this left one, that where we can able to control the biodegradation rate, and then we will be able to know the drug concentrations at the blood streams for effective control. Okay, next, please. Yes, I mean there are different nanoparticles used to control the drug, to understand, I mean mechanistically understand the situation, so I'm not going into these details of this, but the way is by using different nanoparticles we will be able to control the biodegradations and thereby control the drug release from the systems. Next, please. I mean this is, we developed some hydrogels, and there are two types of hydrogels influenced by the nanoparticle, and we change this chemistry of the molecules, and thereby we can have different types of hydrogels, and where we can embed our drugs, and they can release the drugs slowly for this delivery to the systems. Next, please. This is just to show the morphology of these the drugs embedded in the systems. So next, please. This is a system we developed, that injectable hydrogels by using some polymers, where we can embed the drugs, and then the sol we can input into these animals, and then that will be formed gel within this body, and then particular locations it will be release the drug at particular sites. So this is a kind of a controlled release systems using these hydrogels, and we have developed this chemistry and influenced by the nanoparticles also, which can control the drug release into the systems. And these are the kinetics here, how we can change it. So next, please. This is one of the interesting systems. This is the layered materials, two-dimensional layered materials, where we are hiding the drugs within the nanoparticle levels or nanoparticle gallery, and by that way we will be able to release the drug at a very controlled speed. And then we have applied to the cell biology and the actual breast cancer models in these mice models, and then we can effectively shown that if it is pure drug which killing the cells very less, and on the other hand most of the drugs are basically damaging the liver. The right side part, I mean this part you can see is damaged liver here, and as opposed to the normal liver morphology. Very nice, thank you. So the normal liver, so the normal liver is there if we have a delivery systems or effective delivery systems. So that's the development using the nanoparticles. And this is basically a layered double hydroxide kind of nanoparticles. So next please. This is the systems. If we further complicate these things, we embed the drugs within the nanoparticle, and further we have embed into the polymeric systems. So we have a double protections or double diffusion layer to say, and which effectively controls this release rate from a very high rate to the low rate, and that's the. And then we have found that how it affects the cell biology and the animal model systems to control the disease. Next please. Next please. Okay. So this is another delivery systems where we are polymerizing this material within the nanoparticle layers, and then we are putting the drugs into these systems. So next please. And this is how we can control the cumulative release by embedding the drugs at the different systems. We have 1, 2, 3, 4 systems, and 4 systems have different drug release, the profiles, which controls the concentration of the drug in the systems. So next please. And this is just the schematic behavior and the chemistry that we perform. I will not go into the details of this. Next please. Okay, so this is one systems, interesting systems. We developed this copolymer, so-called graft copolymer, cyclodextrin and the. Okay, see you. Thank you. So we have the graft copolymers and many different the approach that we have taken. One is this grafting from this side, and another is the very complex 3D structures, or sometimes it is a linear molecules, and then there is a graft polymers. Now, all the way is to control the drug release concentrations or profile. By that way, so what is important that other than the cell biology, we put it actually generate the cancer, mostly they are the skin cancers, and then we apply our formulations here, and we found that if it is the pure drug, it basically affect the liver severely. But if it is the same concentration of drug, if it is in the formulations, and then our liver is very normal, and on the other hand, we can control the tumor volumes almost to the 0 level. That's important part, using the new systems, which are mostly this very complicated one, the structures, and there the advantage is there are lots of spaces where the drug molecules can be hiding there, and they can be released very effectively and slowly. That's the important aspects. But anyway, we will be able to heal the cancers or the tumors, it is melanoma cancers, and effectively it can be controlled without damaging the other body organs like the livers and spleens and other parts. Next please. Next please. Okay, so this is another system, so where we put the linear molecules and then grafted the polymers, and then the ideal kind of drug release behavior is observed in this case, and here is also we can able to control the tumor size effectively, and the reason for this is controlled by the cumulative release of drug. So this is a animal system study where we can show that the formulation is showing very high concentration of drug at very longer period of time. So that's the reason for this efficacy of the systems, that why it is effective without damaging the other body organs like livers and other things. So next please. This is the orthopedic implants. I mean, we collaborate with the orthopedic surgeons at the BHU hospitals. What we do that MRSA is the staphylococcus. I mean, it is a dreaded things, and we induce it to generate the kind of the infections. And if we use the vancomycins and we put this, this is our tiny implants where the drugs are there, and they can slowly release from the systems, and we can see instead of infection in the control systems, and there are bones which are growing very nicely. Okay, next please. And here we can see that, this is the polymers which is gradually dissolving or bioabsorbed into the systems, and thereby it release the drugs from the systems, and at the end of 45 days we can see here there is the implants or the polymers are disappeared or dissolved out and releasing the drug continuously, and then we can expect that there will be no infections during that period while we are developing or we are healing the bones for the systems. Next please. Okay, so there we have designed the sutures and the stent based on the concept of the shape memory effect. Shape memory, the materials which can memorize its previous shape. I am not going into the science behind it. It's basically the dancing of some part of the molecules. Whenever we are changing the temperature, some part of the molecules are dancing from here to here and going back. So that's the essence of this same memory, the polymers. We utilize this concept to develop the sutures and the stents. Here, sutures we use these polyurethanes, and where we made the drugs, and then instead of stretching it out, what is the usual practice by the doctors, so it is slightly heated using the hair dryer, and it automatically memorizes its shape, and then it is connecting the two tissues from two sides in just 6 seconds without giving the pain to the patients. So that's the advantage of it. One, and another part is we can use it as the stent material. So where we put the stent here, and then this is a tube, and if we put this at slightly high temperature, at physiological temperature, 37 degrees centigrade, so it is memorizing its previous shapes, so it is covering the whole cylinders, and then it can be used as the stent materials for disease control. And we are trying to put it for the colon cancers and other things now. Next please. So this is our one work where we did some work from almost lab to the bed scale. So this is a Ayurvedic drug. It has been long used by the Ayurvedic doctors. It's called the Panchavalkala. So, but the Panchavalkala could not be stabilized for a long time. So what we did, being chemist by myself, and what we did, we stabilized this material into some, using some the chemicals, and I think there is some problem in these images. But anyway, what we develop is the gels and the scaffolds, where we can embed the different these drugs. Say, and then we will be able to release the drug kinetics at particular conditions. And these things are being applied for these animal systems, and where we can say if we use some scaffolds, and then it can heal the wounds in maybe less than 10 days, while usually 14-15 days are time required for the control systems. The fundamental reason behind it is lies in these scaffolds, where it is a porous in nature, and aerations and pass out of the pass from these wounds is very easy. That's the basic reason behind it. And we applied the scaffolds to many patients at BHU hospitals. They are very happy that this materials is actually peeling up easily as compared to the dressing metals now available. So, and next slide please. This is very scary, but this is actual patients which is conducted by Professor Manoranjan Sahu at Banaras Hindu University. So this is a very large wounds, and it is covered with these our scaffolds, and we can see that they can be completely healed in a little bit longer period of time. And let me tell you that those patients are severely affected for a long time using other medicines, and then they come to Professor Sahu for treatment, so they are very nicely healed. So the size of this, the wounds are most often more than 6 inches, that much of big size of this one. So that can be healed also without any problem. And we have several trials also at different locations at Sri Ravi Shankar's hospital. We are done. Ravi Shankar's hospital, and they have also tried to do it in many different ways, putting it snake bite case and other cases also. So they are also being healed nicely. Okay, next please. So this is, I mean, I don't like to emphasize, so this is on the mechanistic way how it works through this the cell biology and the animal model study, and some of the things we are doing it as the TNF alpha, which talks about scientifically that inflammation is there or not. Next please. So this is, I mean, the BHU has a very big dairy also. So we put the wounds, our latest development is the gel, and we put them into this one, and we can see that there is a healings in say around 25 days, in sometimes in 44 days, but that depends on what is the size and type of the wounds. Some of the wounds are very infected, and some of the wound size is large, so that is the factor. And then, but we found that okay, around 20 to 60 days is the time for getting healed of these different types of the wounds. Next please. I mean, I think there is another way. So we have a comparative study. So disbudding, or it's called the disbudding is this word, or dehorning is this. Sometimes nowadays the people are removing the horns at the early stage, and we have a comparative study. Doctors nowadays use betadine is the standard material, and in one case we use the betadine, and another case we use our formulations, and this is the relative healing rate. What we found in our case, and most of the cases are relatively getting healed at faster as compared to the betadine we used it. So efficacy is proven with the systems. We are trying to commercialize this one with one company. Okay, next please. So this is that our development of materials aspects, different types of material that we develop, and for the healthcare treatments. So this is the better life for using better materials. Okay, thank you for your patience. Next please. Okay. So these are the pillar of so they did everything for us, the students, and with some funding from CSIR and Tata Fellowship and so on. So I'll be happy. Professor Misra is eager to more on discussions. So I'll be happy if there is any questions, queries, or comments and so on. So we can
thank you, Professor Maiti, for wonderful lecture. And here we requested all speakers to limit in the time. I first told for 5 minutes, then some people they say, no, make it at least 10-15 minutes. So we just changed to 10 minutes lecture, and then 10 minutes discussion. Students will ask questions, and the good questions who will ask, they will be awarded Intelligent Student Award. 5 Intelligent Student Award will be given based on the questions they will ask. Okay, so I request all the students to take the opportunity to get Intelligent Student Award. So this first time I think introduced in India. In Europe it is there, from that only I learned. So please ask questions if there is. Thank you. Any question from anybody?
So bombard the speakers with your questions.
Delegates also can ask, but no award for the delegates.
Please, madam. Madam, please.
Mike.
Thank you so much. It was really a very interesting, and the diverse application of your technology, it's very good to know. I was just curious to know, why did you name slow release 2D nanoparticle? So I thought nanoparticle is 3D, so why you are calling it 2D?
This is, madam, in 2D because it has X and Y. Z axis, Z dimension is around 1 nanometer.
Okay.
So that's what we call it as this 2D. So the good example is the clay and layer double hydroxide.
Fine.
So one layer thickness is around 1 nanometer.
So reducing one dimensional is giving additional advantage?
Yes. Additional advantage means we have a layer structure
Right.
So we can put the drugs within these layers. So that has the advantage.
Right. So, drug loading capacity is increasing if you reduce one dimension.
Yes.
Perfect. Thank you so much.
That's, I mean, other than the interactions, I mean, that also hiding effect is there. And if it is the polymers, I mean, there is no hiding effect other than the free space in the polymers, so-called pre-volume of the polymers.
Thank you.
Okay, thank you.
Oh, acha, please.
Sir, first of all, thank you for your wonderful presentation. I am curious to know, like, whenever such healing essay has been done, then how your material was applied on the wound? Like, what was the strategy adopted to retain your drug components there on the wound for quite a longer period of time?
Yes, I mean, the most effective way is the putting the scaffolds. Scaffold is like a kind of a the cotton pad. It is basically like a cotton pad, and we can put anywhere in the body parts, and I mean, it will be there. And in our case, our Professor Sahu, most of the cases he studied or he kept these pads in actual patients for 3 to 4 days. And 3 to 4 days, it is gradually releasing the drug. And we have kinetics also, I mean, in vitro kinetics. So that also says around 3 to 4 days release.
So, I mean, while the healing process was done, the material was retained there and gradually got degraded.
Yes. No. I mean, after 4 days, the scaffolds we are removing. Okay. So after every 4 days, we are putting another scaffolds.
Okay.
But the greatest advantage is whenever we are changing the scaffolds, it is not giving pain as compared to the gauze and the normal leucoplast nowadays being used. Okay. So it is taking up the newly grown tissues, which gives pain. So that pain is not there actually. That is the good part of these materials.
Thank you, sir. Thank you.
And the healing rate is also fast, as we are not disturbing the newly grown tissues. So healing rate is also fast.
Okay, thank
Hello,
you. Please, your name,
hello.
please. Sarkozy, your name, please.
Madam.
Dr. Sanjeev Mehto.
Professor G. Mato. So please introduce first, then you ask question, okay?
Sure.
Yeah.
Sure, I'm Durba from IIT Ropar. So actually my question is, first of all, thank you so much, Professor Mahathi, because you have developed different type of delivery systems for releasing the drug. It is very interesting talk, and actually I'm just curious to know that you are, these systems are only for releasing the small molecules, means drug you are considered as a small molecules, or also oligonucleotides also?
Yes, I think it can be nucleotide also. So any drug, which is better to say, diffusionally controlled, that can be done. Say if it is even very large molecules, we can have a different delivery systems where the delivery material can be degraded. Say like biodegradable scaffolds and other things. So then erosion will take place, and even if it is very large molecules like even the nucleotides or other proteins also,
yes,
they can be also released.
Okay.
In fact, any molecules can be released.
Okay.
But we are mostly concerned about the cancer biology, so we are mostly focusing on this one. We have one work on the p53 proteins to gene repairing, another case. So then our problem is the negatively charged molecules, they cannot go inside.
Exactly.
So our tricky way of doing it, if we embed it or hide it into the two-dimensional particle or the polymers, and then we are nicely play with the charge characteristics, say positive, negative, and then they can go adhere nicely onto the cells and go inside.
Sustained release is there.
Yes, and then transfections and other mechanism will operate within the cell systems.
Okay, thank you.
Thank you. Any other question from the, a lot of students now raising hands.
I will be happy, maybe I can go.
So now intelligent students will ask intelligent question.
Hello sir, thank you for your nice presentation. I want to ask a query.
Your name please?
I am Balram Misra from NIT Roorkee. I want to have suggestions like, can we really control the release of drugs? Like I suppose I need a 10 ppm or 10 micromolar. Can we really do that?
Yes. I mean, by suitably controlling the system, so you can able to do whatever you like. Say, for your disease control, if you need 1 ppm, you can do that. Say how much initial concentration that you are doing. Say instead of 1 ppm, you can go for 100 ppm, and then you need to embed, say maybe 500 ppm initially, and then gradually they will be delivered out from the systems.
So for that we need like multiple injections.
Multiple
injections like.
Multiple injection.
Yes, sir.
No, not yes. I mean, you can do it intravenous also, no problem. I mean, say in that case, you have to design. I mean, we have also designed, say the small particles, and within that particles, you can embed your drugs, and depending on the requirement of yours, so you can exactly embed the drugs amount. So you said around 1 ppm to 100 ppm. So that depends on the say level of injury and the level of the disease and so on.
Thank you, sir.
Hello, sir. Thank you so much for your talk. It was really, I learned a lot. I'm Ashwini from NBIL, and my question to you, I have 2 questions. The first one was for the dehorning wound healing application. How do you compare it to just topical application? Because it's on its surface level, right? So
Dehorning. Oh, dehorning is a very unique case. That's we have the 2 horns, and the system is absolutely the same, left and right horn. So here, one we treat with the existing materials that we have, and now the doctors are using most often for antibacterial medicines like the betadine. And then we use 1 horn after the wound is created. 1 wound we create the betadine. Another one we created with the our formulations. So then it is actually the same systems, same immunological systems where we can compare effectively. That's the advantage. I mean, not like the cow, we have say wounds here, and another cow, another wounds, but their immunological systems are different. We cannot compare.
Right.
So here we can compare with existing things. And now we are trying to the commercialize. Let us see how it works. Somebody is interested to see their development with our developments also and so on. But it can be used nicely and compare for these disbarding systems. But wound system we cannot compare. I mean, we can see that, okay, but now we have developed some mathematical the solution for that, and at what rate it is healing the rate. And there are some kinetics we fit into the machine learning systems, and then we try to predict it at what are the levels of healing.
And it shows that it's better through nanoparticles or through your wound healing application, like the advantages are shown?
Yes, nanoparticle or polymer, I mean, it depends on the drug delivery vehicles we use. Sometimes we use nanoparticles, but for this wound purpose, mostly we use the polymers.
Okay.
Polymers has the advantage because nanoparticles, they can be wiped out, but the polymers, they can be sticky over these systems. So that is the greatest advantage in the form of gels and other things.
Right.
Somebody like to make it spray. We also develop spray using the same compositions. A spray is preferable, but not the best. The best one is the gel because that can be adhered onto the skins for a longer period of time. That's better.
Okay, I understand. Thank you so much. And with the nanoparticles, were they targeted drug delivery? So if I will require a certain tissue type, would it adhere to that certain tissue, or how does it work?
Yes, I mean, what is our way of targeting?
I interfere, means you can discuss, you are here, but please give the opportunity to the students. They want awards.
Please feel free to.
Any student? Any question? On the student only one I got response.
May I ask?
You, yeah.
Yes. So in the dehorning part, you said a part is treated with scaffold, and on the other part we are using this topical application of betadine. So the scaffold is changing every 4th day. So are we concurrently doing this betadine dressing part and maintaining the whole atmosphere?
I mean, in that case, actually, we change it. For the patients, we do change it every 4th day. But for the dairy system or animal system, every alternate day.
Okay.
And we also apply the betadine alternate day also.
So the application is again in a topical format, or like when we place that scaffold, we clean it and we place it a fresh scaffold. So is the case same, like is it comparable or impactfully comparable while comparing it to this just a topical application of betadine and the scaffold loaded with drugs?
Yes, I mean that can be compared nicely because I mean you are comparing with a proven systems, or betadine is a proven systems that now doctors are used. So some cases most of the the doctors try to apply the advice maybe alternate day or after 3 days of time, and then the cleanliness, we need to go to the hospitals and somebody will be doing this job, say maybe 2 to 3 days time. So their case, I mean, it is much better. Our systems that, okay, 3-4 days you don't need to take care of, and maybe after every 4th day you go to hospital and change your scaffold.
So I was just curious to know that like the scaffold, a controlled release of betadine would have made the difference lesser?
Actually, that's our main advantage is to apply the Ayurvedic drugs instead of betadine. That's the main goal actually.
Oh.
I mean, when you start this problem, I mean, utilizing the herbal drugs on different forms to control the disease. But by that way, we should show that how the existing drugs should work. I mean, then only we will be able to talk about its efficacy. But the main goal is to apply the herbal drugs. I mean, in this case, because we are collaborating with the one famous scientist, or I mean, this year he has been awarded a Padma Shri award also. So we feel very fortunate to work with him for I think last 10 years or so.
So the last one, there's a calculation of pain. You said it's less painful. So how did we quantitatively assured? Is that just the behavior of the animal we are treating?
No. No, I mean, it's the nature of the scaffolds. I mean, it's not sticky because it is processed through the electrospinning methods, where the molecules are oriented in one direction, and thereby they are very nicely crystallized. So once they are crystallized, they are not sticky to the wounds. If they are not sticky to the wounds, and they can peel up nicely. But on the other hand, they have a sufficient interaction with the wounds, so the delivery of drugs can take place easily. That's the advantage. Our drugs should be delivered nicely. So then there should be a nicely interactive systems, but it is not so sticky to the wounds.
To cause pain or to damage the tissue.
Yes.
Thank you. Thank you so much.
Oh, one last question, any student if they want to ask. So, okay, I think no question. So, thank you, Professor Mahe.
It's my pleasure.
So, I request all the speakers to limit their talk maximum 10 minutes. And students who are interested to ask questions, I encourage the student to ask because they can get the chance to get Intelligent Student Awards and 5 number of awards. So you have ample opportunity to get this award. Your CV will be stronger by the Intelligent Student Award. So please listen carefully, prepare the question and be. Thank you.
Thank you for the informative talk, sir. The next speaker, Dr. Chinmaya Mahapatra. Dr. Chinmaya Mahapatra is an assistant professor from the Department of Biotechnology, NIT Raipur. He did his PhD under Brain Korea Fellowship, and he pursued his postdoc from IISc Bangalore and also from Helmholtz, Berlin, Germany. He was also a recipient of Korea Research Fellowship 2020, awarded by National Research Foundation, South Korea. He then joined as a project scientist in Samsung, South Korea. His research interests are in biomaterials, tissue engineering, nanotherapeutics, nanoplasmonics, and redox nanomaterials. We cordially invite you to the stage, sir.
Thank you for the invitation, and I'm thankful to Professor N.C. Mishra sir and all the organizers for these events, and I'm again thankful to the senior faculty members, students, to listening to my talk. Can you start the presentation? So today we'll be discussing about the one of the very fundamental chemistry related to the biological application, that is redox nanomaterials. So what are the redox nanomaterials? These are the nanomaterials that can scavenge ROS in a simple term, and we'll see how can the simple nanomaterials can be therapeutically effective in various disease scenario. Next slide. Serum nanoparticle in very simple way can be elemental chemistry. We can explain by having particular valency states that can scavenge the ROS. This is all the chemistry part. And next, we'll go to the next slide. So by scavenging the redox or the scavenging the ROS, we can target cell-metal interaction, cell-cell interactions, cell migration, inflammation, angiogenesis, and tissue-metal integration. These are the key stones for tissue regeneration and how the material can integrate with the tissue. If tissue remodeling is needed and then there is high ROS and fibrosis, we can use this type of redox nanomaterials and target this particular area like fibrosis, functional, dysfunctional of the biomaterials to get a tissue regenerative responses. We will see in the course of our presentation. Next. So what happened? What are the target areas that can be focused with redox nanomaterials? These are some of the potential target areas: neurodegenerative diseases, cancer, cardiovascular, ischemia, diabetes, and arthritis and other autoimmune diseases. Of course, I'm not going to go through all this because of the limitation of the time, but at least 2 disease models will show you how the therapeutic effect of the nanomaterials can be seen. And in case of the cellular response, if you have you can scavenge the ROS, you can protect the cells from the lipid paradox, and protein and DNA fragmentation based cellular marker. Next. Okay, next we can go. So what we did, we produced cerium oxide nanoparticles using the hydrothermal method. There is a very core established methods and Oswald ripening chemistry to get different type of nanomaterials, because we are just targeting single nanomaterial and we want to see the morphology of nanomaterials and their therapeutic effects. Does it have any effect with its therapeutic response? Next slide. So we have produced different type of nanomaterials, starting from the different aspect ratio from the nano particle to nanorods and nanowires. Next slide. And what we found that indeed that nanomaterials shape and size affect the cellular response and the cell behavior. And you can see from the cell migration data and other types of in vitro data that we were true in our hypothesis. Next. So when we see the cell internalization also, the cell response to different nanomaterials and the internalization is different for different nanomaterials. Next. So we have seen that cerium oxide, next slide. We have seen that cerium oxide nanoparticle, because of small aspect ratio, can internalize quickly to the internal organelles of the cells, whereas the nanowire and other types of high aspect nanoparticles, they stay outside of the cell and then they provide the therapeutic effect something outside of the cell. So next slide. So we have seen that in vitro result that up to a particular therapeutic dose, the nanoparticle can be indeed therapeutically effective in scavenging the ROS. Next. So through different assays, we have come to know that cerium oxide nanoparticle can protect the cells from ROS-based damage, and then that can protect the nucleus, the nuclear DNA fragmentation, lipid peroxidation, and other type of protein oxidation. These are key markers for the different types of components in the cell. Next. So what we saw that different type of nanoparticles, they can internalize, they can stay outside the cell and then provide the therapeutic effect according to the shape and size of the nanoparticles. In this case, the redox nanoparticle, that is the cerium oxide next particle. So we went through seeing our therapeutic effect of the nanoparticles in two different type models. That is the spinal contusion injury model and the hind limb ischemia model. Next. What happens in the spinal cord injury model, that we put a particular weight on the spinal cord of the animal to cause the injury, and we went through the different time series of the assays to see that from the late to the early markers, how the cells, the particular injury model responds to the treatment of the nanoparticle. Next. So when we applied your cerium oxide nanoparticle to the cortical neurons, we used the nanoparticles, so they got internalized. It is single shot treatment, not multiple. And we can saw that it protects from the H2O2. Next slide. The protection of H2O2 caused the significant reduction in the INOS. It is a particular marker that is significantly prominent or dominant in case of the ROS response in neural cells. Also, we saw that the particular axonal marker SM1312 that was consistent throughout the dosage. And next slide. So by tissue histology and other types of assays, we came to know that the cerium oxide is able to downregulate the production of INOS and protect the axons and other neural cells from damage from ROS. This protection from ROS or scavenging of ROS caused the synapses formation, and the axonal communication is restored in this case. Next slide. So we got the solid evidence that indeed ROS can be very much beneficial, scavenging of ROS and application of cerium oxide nanoparticles or other types of redox nanomaterials. I'm not only focusing on cerium oxide. Why I'm focusing on cerium oxide? Because it is single component and we can reduce the therapeutic value in its purest form. And then we come to know that indeed the cerium oxide nanoparticle in dose response manner was indeed therapeutic in restoring the spinal cord injury model. And we also have other data of the mobility of animals, but I couldn't show here due to the shortage of time. But indeed the animals were able to recover and they could walk after getting the spinal cord injury. Next slide. So these are some of the markers which are pro-inflammatory and inflammatory natures. And due to the downregulation of INOS, lot of inflammatory markers were downregulated, and significantly there is upregulation of pro-inflammatory markers. So conclusion is, when you inject cerium oxide nanoparticles in a single dose, it can have the effect in gene regulation to downregulate various oxidative stress-related markers, gene markers. And also due to scavenging of ROS, it can have neuronal cell growth, axonal regeneration, and thereby causing the functional recovery. So we also evaluated that ROS is a very significant component in restoring the angiogenesis or the blood vessel, how the blood vessel can connect. So ischemia, as known, is one of the disease state where the blood supply is discontinued in case of the tissue. So due to the discontinuation of the blood supply, the tissue undergoes necrosis, and finally the functional loss is there and tissue is lost. So next slide. So we developed the model of hind limb ischemia model, and we injected our nanomaterials, cerium oxide nanoparticle, different dose format. And due to the scavenging of ROS, there is restoration of the blood supply, as can be seen from Doppler images. This Doppler images indicate the restoration of blood supply by induction of new angiogenesis. But there was a critical thinking in your mind how the angiogenesis is promoted, which pathway. Next slide. So these are the tissue responses, and if the if you can see in the slides that cerium oxide actually get retains in the muscle tissue, because muscle tissue is a type of tissue that can retain the different drugs, or it can slow the release of different drugs. Cerium oxide retains in the muscle tissue, as you can see from the biotech, and provide these therapeutic values. Next. With we also come to know that when you downregulate ROS, there is also production of endogenous angiogenesis markers like beta, BFGF, VGF, and SGF. So this endogenous production of growth factor from the tissue itself is healing the tissue.
Thank you.
Hello. It was a nice talk. One question I was having, not question, rather, it's a kind of, I want to understand something, that because it has this, is it selective towards cancer cells? Because this cerium oxide itself.
Yes, yes.
Does it
there are
have
some
any
reports that cerium oxide, due to this ROS,
yes,
can kill a lot of cancer cell.
Okay,
I have seen the reports in case of lung cancer and other types of HeLa cell type of reports, but we have investigated the therapeutic outcomes.
And does it, is it toxicity? Have anyone measured, of course, the toxicity profile of these?
My personal opinion is anything from outside in body is toxic, but it is what amount we take. Even, right? If all are IITians, then somebody from outside will feel insecure that I am not from IIT. So something happening in case of in a very simple way I am explaining you, Oswald ripening. So nucleation and growth depends upon the supersaturation nature of that particular salt, and the protons actually assist in the nucleation growth kinetics. This, if you have a book on that, you can get a flow of how this particular help in the supersaturation and the G value of the radius. So these two things you should always read, that is the Oswald ripening and the GRIGC based nucleation and growth of the nanoparticle.
Thanks for such a nice presentation, sir.
GRIGC is grain rotation. Okay, just read.
Sir, I am Divya from IIT BHU. Sir, I want to know, in one slide you have shown they are showing neuro regeneration part.
Yes.
So the administration of these particles on the damaged site directly, or there is another type of administration of this particle?
Directly to damaged site in a single shot, just one time.
So sir, like how much time it will take to regenerate neuron? Is it connecting with ECM or the cell? Like how much time it is taking to recover this part?
We have shown in the study that we have studied, whenever you do an in vivo study, you keep a initial time, that is in hours, inflammatory, and then you go for days, and then you go for month. So we have observed within 4 to 6 days that axonal connection is happening.
So 4 to 6 days at the spinal cord is damaged, or
Yes,
it
yes.
is fully damaged. So animal is surviving with it.
Animal is, the particular model, if you go through the literature, we are dropping this is called T2 weight or particular weight, we are dropping on the spinal cord to cause a half injury.
Okay.
So the animal is paralyzed.
Achha,
It is surviving.
Paralyzed.
Yes,
And
yes.
after that neuro regeneration.
We do the BBB score based walking test to see the locomotor recovery. It is known as locomotor recovery assay to see how the animal can walk. So there are fixed protocols to follow to do those tests.
So I want to know the shape. Is there any future aspect that we can load any drug with these particles that is also helpful for
Yes,
neuro-
people are now loading different types of drugs
So we can load drugs with it.
that can promote neural filament outgrowth and connectivity, the synaptic connection.
Synaptic. Thank you, sir.
Hello sir, thank you very much. I am Pawan Kumar Pandey from IIT Roorkee, and I want to know that you have shown the different applications of cerium oxide nanoparticles in nerve tissue engineering. So I am curious to know that is there, they have the ability to cross the blood-brain barrier also?
In case of nanoparticle?
Yes, these cerium nanoparticles can cross the blood-brain barrier also?
We have not done that study, but I have heard they cannot cross.
They
people have modified that nanoparticles to cross the blood-brain barrier because the macrophages will capture before it can go to the blood-brain. Blood-brain barrier is very strict zone. So the nanoparticles will be captured by the different types of inflammatory systems in the...
So we can apply these nanoparticles via external applications just. We can't
Yes.
go through the...
We inject externally.
Okay. And sir, just a curiosity, that is there any other type of nanoparticles rather than cerium oxide as an example of a redox nanomaterials?
There are many types of redox nanomaterials coming under this particular transition metal groups. Vanadium oxide has been published in Nature publication by ISC Bangalore. They have worked on that. It is just the play of the valency state, how much higher valency and the capacity it has. So cerium oxide is now, I think, is well established because already there are many pharmaceutical products like burn care, medicine, topical medicine already with the cerium oxide nanoparticle inclusion. Other materials, I don't think they've still come to the market to be applied. But cerium oxide exhaustive study has been done in case of therapeutics.
Thank you, sir.
Yes.
Yes.
Hello, sir. I am Salman from IIT Roorkee.
Yes.
As you mentioned in their slide, my question is that what is the mechanism between this the lipid peroxidation and protein peroxidation, with effect of that is the cell structure and their in tissue engineering?
So if you want to understand the basic concept how the cell necrosis or cell death will happen,
Yes.
it is due to the destroying of the different structures of the cell. The cell is made of protein, DNA and lipids. So under the high ROS, the reactive oxygen species, this particular micromolecules or macromolecules undergo changes.
But you mentioned that this is a lipid peroxidation. It is the different from the other oxidations, या फिर both are the same thing, sir? What is the lipid peroxidation, sir?
Lipid peroxidation, you have lipids in your body.
Yes, sir.
So when they got oxidized, they change their biomolecular activity.
Yes.
Right, a molecule, a small change in molecule also it will change its molecular activity.
Yes, sir.
So that lipid, if you go through the funnel chapters of the lipid, it is composed of different type of components of lipids.
Yes, sir.
Aldehyde based, other types. So when you have more oxygen or free radical, so after you get high ROS, this get damaged and these are responsible for the factors for cell death.
One more question is
So, bit about that I don't know.
Yes, we have published one article on that with the collaboration with ISC Bangalore. We used cerium oxide nanoparticle in a matte format, and we saw that the neonatal cardiomyocytes from the mouse, they could survive more on that because cardiomyocytes are muscle cells and basically they function on calcium uptake the channel, calcium channel. So cerium oxide assists this neonatal cardiomyocyte to survive longer outside the body, and this patches has been put on the damaged hard surface, or cryo-based damaged, like we use ultra-low ice to damage the cardiomyocytes and then we put the patch. So we have used cerium oxide-based mats.
Okay,
for nanofiber.
sir, as you mentioned that it is somewhat related to like calcium ion uptake and somewhat, there is a condition known as aneurysm in which there is seen that if there is like high blood pressure condition and in that condition the thinning of blood vessels is seen. So
Yes, yes.
there are chances of like rupturing of the arteries and like it can lead to like deleterious consequences in the patients. So is it possible to use a combination of redox material with some like combination of calcium to treat that condition also? Like in that condition, if it can like have some role that like these patches can actually be used like in that way that it can actually prevent that rupturing. of-
Hypertension.
Yes, not hypertension, not hypertension. For like we know that calcium ion also have the role in coagulation of blood also. So if it can in some way prevent the rupturing of the arteries in that case, and it can like have like role in the treatment of that particular.
Well,
disease.
without study, I cannot solidly claim about that particular, because a true scientist cannot postulate things.
Yes.
But we surely can look forward in future about that particular application. But
Yes.
I am not so confident in telling that it can function in that way. But looking at all the possibilities, maybe there is chances.
Okay, thank you, sir. Thank you so much.
हो गया ना sir?
Hello, sir.
Any other question,
Thank
please,
you,
please.
sir. Myself, Dr. Ravi Prakash from IIT BHU.
Yes.
Sir, my question is that how to size effect of your nanoparticle with your result?
How to?
How to size effect? I think a particular size show the particular effect either increases or decreases with your result.
Yes.
Have you checked, sir?
How to correlate?
Yes.
So I have shown here now. We use the different type of nanoparticles, and cellular. We have seen the different response of the cell because of the uptake, and we have gone through investigating cerium oxide, just the smaller 20 nanometer nanoparticles. We are investigating other nanoparticle in.
But sir, people are also reported that 20 nanometer particle are also show the lungs cancer in 2026.
Cerium oxide.
Yes, cerium oxide nanoparticle.
Maybe the dose is depend upon the how much dose they are using.
Sir, in your case, how
We are
much
using very low therapeutic dose.
Okay.
According to the weight of the animal, we are calculating the dose, and we are keeping it beyond lower than the permissible pharmacokinetics doses that is already prescribed by the FDA.
Okay. Most of the sir, group R says that cerium oxide is toxic in behavior, but I think 20 nanometer is
Actually, all nanomaterials may be toxic if you take
yes,
it in
yes,
the way.
yes,
But,
but
we
my-
are using aluminum foil for food also.
Yes.
So
But sir, my question is that if you increase the size, I think you choose the 20 nanometer. But particular research group show that these sizes show the lungs cancer in humans. So my question is that what kinds of property you have to choose for your work?
So one way, if you are concerned about that type of effect of the nanomaterials, you can immobilize nanoparticles on particular substrate or scaffold. So it will not go into the bloodstream and then get bioaccumulated in the lungs and cause those types of lung cancer. So we can make some hybrid nanomaterial bioscaffolds.
Okay. Thanks. Thank you, sir.
Okay, thank you. So now we end this session, and now I request you all to proceed for the lunch that is inside Paramarth Niketan. And we have representative there. You will see we have other reservation counter, and there only you will get lunch. And then dot 3 o'clock we will start again here, 3 to 5 p.m. This will continue. Okay, thank you.
Thank you.